Hello everyone, welcome to Physics Chapter 2, Lecture 2. You will need, in this lecture, your notes. We're starting at the top of page 3. Your book, page 56. You'll need a calculator, and it might be helpful to have a highlighter. So let's take a look at the top of page 3. So free fall is when an object is falling solely due to acceleration provided by gravity. All right, so if I drop this highlighter onto my whiteboard, what made it fall? Gravity made it fall. And you've got to memorize the gravitational acceleration constants. Now, these are true near the surface of the Earth. And when I say near the surface of the Earth, about 40 kilometers to sea level. These constants are true. Now, they're negative because it's falling. And in physics, going down is the negative direction. So if you're in meters, the gravitational acceleration is negative 9.8 meters per second squared. If it's just there's no other force acting on it other than gravity, and sorry about that, if you're in feet, it's negative 32 feet per second squared. So you absolutely have to memorize that, just like these three equations we've already learned. Okay, so in the description box, I'm going to link watch a couple of videos linked in the description box. So since we're doing this virtually, I can't really easily. What I usually did in class was I took a big marble and a little marble and I put them both on the ceiling. I got up on top of a table and dropped them. And the students made a guess as to which marble, would fall first. If we had a little marble, big marble, dropped them at exactly the same time, which would hit the floor first. And to some, the surprising revelation is that they both hit at the same time. So mass doesn't matter when it comes to acceleration due to gravity. Gravity acts on all objects the same way. Now, air resistance can be a factor, but a large marble and a small marble, neither of them have very much air resistance. So they fall at that same pace of negative 9.8 meters per second squared. And they hit the ground at exactly the same time. So that's a really cool physics fact. And I've got an amazing video where they drop a bowling ball and a feather at the same time in a big vacuum, and they hit at the same time. So I want you to watch that video. I think it's 4 or 5 minutes long. All right, there's also a video on terminal velocity, which is at the end of the chapter, that I'd like you to watch. So make sure you watch those two videos that we would have shown if this were in class. All right, most of this lecture is going to be me working problems that we call free fall problems. And the first one is going to be 2.7 on page 56. I'm going to go ahead and leave these equations up here. I may end up having to erase them. But 2.7 says, how long will it take a rock to hit the ground if it's dropped from the Leaning Tower of Pisa, which has a height of 54.6 meters? So I'm just going to go through the process here. We know it's accelerate. We're dropping it, right? We didn't put a motor on it and have it fly towards the ground. We're just dropping it. And the height's given in meters, so we're going to use this negative 9.8 meters per second squared. So no acceleration. We want to know time. Okay, time is how long. We know displacement. How far did it fall? Well, it fell the height, which is 54.6 meters, but you got to be careful. It's falling down, so displacement is negative. That's the most common mistake right there. And we know that the initial velocity, the person didn't throw it down, they just dropped it. So it started out with a velocity of 0. So if we want time, we know displacement, we know initial velocity, we know acceleration. We'll end up using equation number 3. Okay, so delta x is equal to v naught t plus 1/2 at squared. This is probably the most common equation used in free fall problems. And since initial velocity is 0, that whole section goes away. So I would have, let's fill in the numbers, negative 54.6 meters is equal to 1/2 times negative 9.8 meters per second squared times t squared. So doing the algebra, t squared, we're going to bring that 1/2 and negative 9.8 underneath. 54.6 meters divided by 1/2 times negative 9.8 meters per second squared. All right, be careful when you put that in your calculator. Use parentheses judiciously and everything, but you're going to get 11.14 seconds squared. But that's t squared, not t, so we need to take the square root of that number, and that is going to be 3.34 seconds. Amazing. If we know the height, we can get the time. All we need to know is the height. If you drop it, you can get the time. All right, let's go on to number 2.8. All right, 2.8 on the next page. Says that in order to determine the height of a bridge, a physics student drops a rock off the side of the bridge and times how long it takes for the rock to hit the water. If it takes 1.4 seconds for the rock to hit the water, what is the height of the bridge in feet? All right, let's write down what we know. So first of all, we know that we're in feet, so the acceleration due to gravity is negative 32. All right. We know time. It took 1.4 seconds. We're trying to get the height of the bridge, so that's going to be displacement. And again, we know the initial velocity. Didn't throw it down, just dropped it. So the initial velocity of that rock is 0. So we're going to use equation 3 again. Delta x is equal to v naught t plus 1/2 at squared. Since v naught is 0, then you'd have delta x, which is what we're solving for, is equal to 1/2 times negative 32 times 1.4 seconds. Don't forget, you have to square that. A lot of students forget to square it. All right, you plug that into your calculator, you'll get a negative 31.36. But do we report heights negatively? No. The height of the bridge we want to report as positive, 31.36 feet. The displacement, indeed, was negative 31.36 feet, but we don't report the height of something that way. So 31.36. All right. Let's go to page 4 on your notes. Well, let's stick with the bottom of page 3 just really quickly. So when an object is thrown straight upward, its velocity is 0 at maximum height. Oh, that's important. Important to remember, 0 at maximum height, for calculus as well. And when it goes back down and reaches its release point, it's equal in magnitude but opposite in direction. So let me draw out what I did here on the notes. Let's say you were throwing a rock up straight up in the air. Right? And let's say you threw it up at 15 meters per second. At the top of its flight, the velocity equals 0 because it's changing direction. When it gets down to where it started, assuming it doesn't hit the ground there, it would be negative 15 meters per second. So equal in magnitude but opposite in direction. So velocity is 0 at maximum height and equal in magnitude and opposite in direction when it gets to the release point. So if it started out at 15, it'd be negative 15. That's really useful information to have as we work the next two problems. So let's flip over to 2.9 on page 59. All right, reading through that one. Says a student throws a rock off the at the edge of a cliff, and you have the drawing here, bottom of which is 120 meters below the student's hand. If the rock is thrown upward with a velocity of 8.7 meters a second, what will the rock's velocity be when it reaches the bottom of the cliff? Okay, let's just write down what we know. So we're in meters, so we know acceleration due to gravity is going to be negative 9.8. Now displacement, remember, isn't distance. Okay, you're throwing it up off the cliff and then coming down, it's hitting the ground. Displacement is just the distance. Sorry about that. Let's try that again. So we've got a cliff. Displacement would be the distance from here to here. All right, so that's going to be negative 120. That's a really tall cliff. All right, so negative 120. So delta x is negative 120 meters. All right, you don't worry about the up and the down part. Okay, because that, if you were calculating distance, you worry about that, but we just want to know displacement. So that's from chapter 1. All right, we want to know, we know initial velocity, you threw it up at 8.7 meters per second. We want to know the final velocity. And it's not 0. What I'm talking about is the instant before it hits the ground. Well, we don't have time, so the equation that you use when you don't have time would be equation number 2. So we have final velocity squared is equal to initial velocity squared plus 2 times acceleration times delta x. So final velocity squared is going to be 8.7 squared plus 2 times negative 9.8 times negative 120. Let's just fill in the formula. So your calculator, if your calculator is nice to you, will tell you that that is 2427.7. Is that the answer? No, we want to know velocity. So we have to do what? Take the square root. Now when you take the square root, you'll get 49.27 meters per second. But is that 100% correct? Well, let's see, it's a rock. The rock is going down. It's going down. So velocity will be negative. Don't make that mistake. All right, must make negative. Since you're going in the downward direction, must make negative. Very common mistake, all right? Your calculator is going to tell you the positive answer because you can't take it won't take a negative square root. Okay, but we got to make it negative. We just got to use our knowledge of physics. All right, let's finish the on your owns up for this chapter. By the way, that last one, that's a very common mistake, to not make that velocity negative. All right, and it's a fairly major error, so you don't want to make it. Okay, let's do 2.10 right underneath on page 59. So that one says a ball is thrown up in the air and reaches its maximum height of 4.5 meters. What was its initial velocity? Okay, well, let's write down everything we know. And the first thing that we know is acceleration due to gravity. We're in meters, so that's negative 9.8 meters per second squared. We know the displacement. It was thrown up into the air, and its maximum height is 4.5 meters. We don't know anything about time on this problem. What is, at maximum height, the final velocity? Well, as we talked about earlier, it's 0 because we are at max height. So we want to know, in this time, what is the initial velocity? So you always want to set up your problems this way. Even if you get something wrong, I can give you some decent partial credit if you will set things up like this. Okay, we don't know time. We're going to use equation 2. So velocity squared, final velocity squared, is equal to initial velocity squared plus 2 times acceleration times delta x. All right, final velocity squared is 0. We want to know initial velocity. And then we have 2 times negative 9.8 times 4.5. Okay, so if we multiply those three numbers out, you'll get negative 88.2. So I've got 0 is equal to V naught squared minus 88.2 meters squared per second squared. All right, so let's move that 88.2 to the other side, and we'd have V naught squared is equal to 88.2. So V naught, take the square root of 88.2, and you'll get 9.4 meters per second. All right, cool. Okay, want to talk about one last topic here before we finish up. And that is terminal velocity. Okay, so you're at the bottom of page 4 on your notes. Terminal velocity is the maximum velocity a falling object is subject to. Okay? And that's due to air resistance. So if you're a skydiver and you're jumping out of a plane, you know, your body has a lot of air resistance. It runs into the air molecules on the way down. So that's going to keep your velocity from just constantly increasing. So terminal velocity, the more mass, the higher the terminal velocity. And So there is a maximum velocity you can achieve when you're in free fall. So I want you to watch the terminal velocity video. I'm going to link that in the description box. So there's 2 videos for this lecture linked in the description box that you need to watch. They're not real long. And that'll tell you everything you need to know about terminal velocity, all right? The last thing that I want you to remind you of, and I don't know that you will be doing this on the homework from the practice problems, but that's the quadratic formula. The quadratic formula sometimes can be used, and it's in this chapter. It's pretty rare, but occasionally you can use it, and that way you can avoid using two different formulas. You can just use one formula. So if you have, it's always going to be with time. If you have at squared plus bt plus c is equal to 0, then the quadratic formula. So you would take, ultimately it's the equation, number 3 could be made to look like that, because you have a squared time in that, and you have the time next to v naught. So you could manipulate that equation algebraically and set it equal to 0. And the quadratic, if you want to solve for time, you'd have negative b plus or minus the square root of b squared minus 4ac over 2a. And you can use this to avoid, you do not have to use it. But some problems, and it may just be in the extra practice problems, but you can avoid using 2 equations. So it makes the problem shorter. So I don't think the book goes through this. He just teaches to use 2 different equations. I'm talking about you would use both equation 1 and equation 3 maybe, or equation 2 and equation 3. But it's good to remember, and I know you use this in pre-cal and algebra 2, but don't want to forget the quadratic formula. Okay, so the homework that goes with this section So chapter 2, homework number 2, is review questions. And let's see, what's the page on that? 60 something, right? All right, 69. So most of the review questions are about free fall. Review questions 2 through 10, but they're very short answer. And practice problem. All right, we did 1 through 5 last time, so we can do 6 through 10 and finish it up. All right, and I do not think you need to use the quadratic formula on this assignment, but you might need to on the extra practice problems. Okay, so that does it for chapter 2. Make sure you watch those videos that I link. All right, I will talk to you next lecture.